Hi everyone, Kevin here with a quick video on mass and mole relationships. I'm going to talk about core problem 6.21. You can stop and read that problem here, but I want to go on and first do a simple example. Here's an example of a chemical reaction. We just have A plus 2B going to 2C plus D. The coefficients in front of the reactants and the products show the mole relationships. So the coefficients are 1 in front of A, so we usually don't show it if it's 1, 2 in front of B, 2 in front of C, and 1 again not shown in front of D. So the mole relationships, if we react 1 mole of A, it's going to react with 2 moles of B. If we want to completely consume all of A, we need to make sure there are 2 moles of B, whatever B is, in the reaction. It's going to produce 2 moles of C and 1 mole of D. So the mole relationships, also known as mole ratios, if we have the ratio between A and B, it's 1 mole A to 2 moles B. The relationship between A and C is 1 mole A, 2 moles C. The mole relationship between A and D is 1 mole A to 1 mole D. The mole relationship between B and C is 2 to 2. And between B and D is 2 to 1. Say we have 2 moles of A. And we want to react that with B, and we want all of A to be consumed. How many moles of B do we need? Well, it's easy. We can just take 2 moles of A and multiply it by the mole relationships. So the mole relationship between A and B is 1 mole A to 2 moles B. So we can set that up as a conversion factor. We put 2 moles B in the numerator and 1 mole A in the denominator. Now moles A are going to cancel, and we're left with moles B as our remaining units, the uncanceled units. And 2 times 2 is going to be 4, so we have 4 moles B. So it's a real quick way to take the moles of some starting product, or starting reactant, and figure out how many moles of the other reactant we need. All we need is the mole relationship, and it'll tell us how many moles of B we need. Say we want to determine instead how many moles of C are going to be produced from 1 mole of A. And that assumes that all the A will be consumed because we have plenty of B in the reaction to consume all the A. Then the moles of C we can determine from the mole relationship between A and C. So again, if we started with 2 moles of A, we multiply it by a conversion factor that we create from the relationship between A and C. And it happens to be 2 to 1. And so we have 2 moles of C for every mole of A. And so we end up producing 4 moles of C from 2 moles of A. So that's how you use mole relationships to make fairly simple calculations of the amounts of reactants needed. That's what we did for reactant B, or products produced. That's what we did for product C. Let's use that same sample reaction now to do another example looking at mass ratios instead of mole ratios. All right, for this we're going to need the atomic mass of each element in the reaction. So the atomic mass, let's say the atomic mass of A is 1. Let's say for B it's 2. Let's say for C it's 2. And D is 1. And of course, these numbers don't really make sense. We don't necessarily have different elements, A, B, C, and D, but for our example, let's just consider these to be the atomic masses of the 4 different species in this reaction, whatever A and B and C and D stand for. All right, we've got the atomic mass. Let's get the atomic mass ratios. Well, the ratio between A and B, well, A weighs 1 atomic mass unit, and B weighs 2, but in this reaction, we have to have 2 moles of B for every 1 of A. So we need to multiply 2 by 2 to get 4. So it's 2 times 2. It's the coefficient of 2 in front of coefficient in front of B times the mass of B, which is also 2. All right, so A to B is 1 to 4. A to C would be 1 to 4 also, because in our example here, C is also has a mass of 2, and there's a coefficient of 2 moles of C for every 1 mole of A. So 1 to 4. A to D would have a mass ratio of 1 to 1. They both weigh 1. Each has the coefficient of 1, which of course is not shown. So let's say we have 1 gram of A, and we want to know how much B we need to pull off our shelf in our chemical lab. How much B would we need to fully react with 1 gram of A? We want to consume the entire 1 gram of A. So it's easy to do if you have the mass ratios, because we know for every 4 grams of B, we would consume 1 gram of A, and that's just our mass ratio, 4 to 1, B to A. So we take our 1 gram of A, multiply it by our mass ratio, and we get 4 grams of B. Now remember, that differs from mole ratio. In the mole ratio case, let's say we had 1 mole of A, we multiplied by the mole ratio, which was 2 moles of B for every 1 mole of A, and we got 2 moles of B needed to react with 1 mole of A. And I'll note that these are A. So does that all make sense? Yeah, so 1 mole of A times that. Let me clean this up a little bit here so it reads better. So 1 mole of A times that conversion rate means we react 1 mole of A with 2 moles of B. 2 moles of B, well, each B weighs 2, so it makes sense that we'd have 4 grams of B for 1 mole of A, just because B weighs twice as much, or has twice the mass of A. All right, so the point here is we can use these simple mass ratios or mole ratios to solve problems fairly easily. Okay, back to our example. We want to know what the mass relationship is between methane and water in this reaction. So for that, we use the mass ratio. So what are the masses? Well, in this reaction, methane is 16. Oxygen has an atomic mass or molecular mass of 32, and the numbers are in the lower left there. So 2 times 32 would be 64 in this example. CO2 is 44, and there's just one of those. But there are 2 waters, so we have to multiply 18 by 2 to get 36. So our mass relationship between CH4 and water in this reaction is 16 to 36. All right, and that's it. That's all it wants in this example. Note that we could do the same thing for the relationship between CH4 and O2 in this reaction. It's 16 to 64. Between CH4 and CO2 is 16 to 44. What did I say last time? 16 to 64 for O2, 16 to 44 for CO2. Hopefully I said that right. Methane to water, we already did, so we've got them actually all covered. So you can use those mass ratios to determine how much of each reactant or product you need or will be produced given a certain amount of mass of one of the other items in this equation. So say the question was, how many grams of methane do we need if we wanted to produce, say, 72 grams of water? All right, so we need 72 grams of water. How much methane do we need to provide as a reactant for this reaction to produce 72 grams of water? Well, we multiply by the mass ratio between methane and water, and we know it's 16 grams of methane for every 36 grams of water. So grams of water cancel. We're left with the uncanceled units of grams of CH4, grams of methane. If we do the math here, it turns out that we need 32 grams of methane to produce 72 grams of water. And we just get that by multiplying by the conversion factor that we developed from the mass ratio. So that's how you use mass ratio. Thanks for watching. Hopefully this helps, and see you in class.